For their kind invitation. So today I'd like to talk about the KM1 model proposed by Kawai, Matsuo, and Yokokura in 2013 for black hole formation and evaporation, or rather non-formation and evaporation. Let's first review a little bit conventional picture of black hole formation. Of course, for a classical black hole, you can have infalling observers falling through the event horizon within finite amount of time. And Hawking told us that if you turn on Hawking radiation, the black hole would eventually evaporate completely. And after that, you would resume the Minkowski space. Infalling observers would still fall into the horizon within finite time because Hawking radiation is extremely weak. So for the infalling observer, you shouldn't feel anything different. On the other hand, intuitively, this is a strange picture. For a distant observer, it would take infinite time for the distant observer to observe anything falling through the horizon for the classical black hole. The distant observer would have to go here, which is future infinity, to see anything falling into the black hole. When you turn on Hawking radiation, the distant observer is going to expect that the black hole horizon is shrinking, which should make it even harder for anything to fall through the horizon. On the other hand, this conventional picture is telling you that it turns out that for the distant observer, it's going to see the falling through horizon faster within finite time. Let's look a little bit closer into this Penrose diagram for the conventional model. On this one, I have the orange curves representing constant R curves. So you have the R equal to 0 curve going like this, and then you can draw constant R curves like these. So if you are over here, a distance away from the black hole, at the instant when the black hole evaporates completely, you're actually going to see the lights from all different values of R coming towards you. So you're going to see all the infalling objects falling through the horizon at the same instant when the whole black hole evaporates completely, going to 0. But there's nothing immediately wrong, it's just a little bit strange. This picture, the one on the left, this is a schematic sketch of the geometry. So if you are far away from the black hole over here with Hawking radiation, you can use the outgoing Vaidia magic for outgoing radiation geometry. But if you are near the horizon, in the conventional model, you have negative energy flowing into the horizon. Essentially, because of the demand of conservation of energy, the picture is like you have energy flowing, positive energy going to the future infinity, and negative energy flowing into the horizon. That is how our intuition is in disagreement with the conventional model. But for many people, this existence of event horizon is a robust feature of any gravitational collapse. But I like to argue that it's not true, because here you see whenever you have the spatial singularity, it's a failure of physics. If you have any UV physics that can make sense, it's going to resolve this singularity. And one simple possibility is that it's like this. I have this red line representing where the singularity was in the semi-classical theory. And then I imagine that there's this dashed curve. Below this dashed curve, the geometry is a good approximation. The conventional model is a good approximation for the region below this dashed curve. On the other hand, the high energy theory, the UV complete theory, resolved the singularity over here, so that above this line you have just the same Penrose diagram as a Minkowski space. so that you can trust the conventional model for large-scale physics without saying that there is an event horizon. The reason is simply that the definition of the event horizon relies on the existence of the singularity. It's by definition an extrapolation toward the past from this endpoint of the singularity. So whenever you resolve the singularity, you can no longer define the event horizon. And in Penrose diagrams, you don't really represent distance properly, so you can imagine that the generic picture for black hole formation and evaporation is just like a Minkowski space, but with some high curvature region over there. And therefore, in all the models, or almost all the models resolving the information loss paradox, they would have not the event horizon, but just the parent horizon. For example, in a paper this year by Hawking, Perry, and Strominger, they had this Penrose diagram, where the dash curve represents a parent horizon. On the lower half, this apparent horizon is that of a black hole, but on the upper half, it's actually the apparent horizon for a white hole. Everything comes out of the apparent horizon over here. They didn't explain it in the paper, but I think this fits well with the firewall story. In the firewall story, they say that if you have a pure state in gravitational collapse, in the beginning, before page time, the Hawking radiation can be treated as quantum near the horizon. But after page time, you have to treat the Hawking radiation like a classical radiation. And it's going to back react to the geometry, so that it's no longer possible to say you have a black hole horizon over here. The black hole horizon, as we mentioned, can be consistent with outgoing Hawking radiation only if you have negative energy going into the horizon. But the firewall story is telling you that you should have positive energy outgoing at the later time. So this horizontal line is the page time, after which you have the black hole horizon. On the other hand, this is the picture assuming you have a pure state in gravitational collapse. In reality, you have a mixed state in gravitational collapse. Suppose you have a heavily mixed state, so that's almost classical. You can imagine that the positive outgoing Hawking radiation would start earlier, before the page time, because it's already mixed. And in the extreme, if you take the limit in which this curve shrinks towards the collapsing dust, then you can have this picture where the white hole apparent horizon appears just around the surface of the collapsing sphere, with Hawking radiation appearing right where the surface is. Now, whenever you have apparent horizon or event horizon away from the collapsing sphere, you would have the information loss paradox, because Hawking radiation appears outside the horizon, and there is a distance between the collapsing matter and the radiation. So you would have to violate locality to transfer energy to preserve information. But if it's like this, then you would have no apparent information loss. This is actually the same Penrose diagram as the KMY model, but we'll talk about that a little bit later. So in several other models, they have similar, although maybe slightly different picture in which you have a parent horizon of radiation. But let me make two comments about these scenarios. Firstly, a parent horizon is well defined only when there is spherical symmetry. So you can't believe that the apparent horizon is a crucial ingredient in the story of black hole collapse. And secondly, Hawking radiation outside the apparent horizon has to break locality to carry information I just mentioned. So I think it would be more, it would be a better resolution if there's a story in which we don't have to rely on the apparent horizon. So let me review two features of the conventional model, or rather the folklores of the conventional model. Firstly, for infalling observer, Hawking radiation is extremely weak, so it should not change the fact that it's going to fall through the horizon within a finite proper time, as if there is no Hawking radiation in the classical theory. On the other hand, this is a strange statement because the infalling observer is not going to know when he's going to fall through the horizon, because there's nothing strange, nothing peculiar at the horizon. This is also what people always say. So from the viewpoint of his experience, if he's going to write down his experience in his notebook, the description is not going to be too different whether or not there is horizon. Another point is that people often say that in the conventional model, the near horizon should be in vacuum, because for the infalling observer, by the equivalence principle, should not feel anything strange, and therefore you do not expect him to feel strong Hawking radiation, although the firewall story is telling you that this, even if this is true in the beginning, it's not going to last long. But anyway, so because of this, they say that Hawking radiation can only appear at distance. And these 2 points are going to be modified in the KMY model. So let me talk about the KMY model briefly. To simplify the story, they made the following assumptions: spherical symmetry, collapsing massless dust in collapse. So the collapsing shell is collapsing at the speed of light. You can think of this as the extreme case of gravitational collapse. So by conventional wisdom, you would expect that there is going to be a apparent horizon or event horizon at the end. And then the Hawking radiation is assumed to be composed of nothing but massless particles. So you can write down the energy momentum tensor for the Hawking radiation easily, and then you can solve the Einstein equation with the back reaction of this Hawking radiation. The crucial difference from the conventional model is that the energy momentum tensor here is taken to be that of the classical radiation from the collapsing sphere. Namely, when I'm seeing Hawking radiation at distance, I extrapolate or interpolate back to the surface of the collapse. And so you have a non-zero radiation at the surface. The conventional story would be that this would, together with infinite blue-ship factor, this would give you a divergent energy flux at the horizon. But actually, if you really do the calculation carefully, with the back reaction taken into account, you are going to say that there wouldn't be a divergent energy momentum tensor. So to see what's happening, let's look at the region outside the collapsing sphere. Outside the collapsing sphere, there is nothing but outgoing Hawking radiation, so you can use the outgoing Weidian metric. It applies to the region outside the collapsing sphere, which is at coordinate capital R. U is the Eddington-Ricciardi time. It's a Lacombe time coordinate, and this is the metric where the Schwarzschild radius A is a function of time. It's 2 times the bumping mass of the collapsing sphere. And the outgoing radiation has this energy momentum tensor, depending on the time derivative of A. This metric tells you that you have these 2 light-like geodesics for outgoing and ingoing light-like curves. And you can just follow ingoing light-like curve to check whether it can fall into the horizon within finite time. By simulation or by analytic analysis, you can easily see that if I assume the Schwarzschild radius to change with time according to the usual formula of Hawking radiation, then any infalling curve, light-like curve, would not be able to enter the Schwarzschild radius within finite time. So I enlarged this portion over here. So after the whole star is evaporated completely, all these ingoing light-like trajectories continue into the Minkowski space, which is geodesically complete. So you see that none of these ingoing light rays can cross the horizon, which means that there is no horizon. Now, certainly, if ingoing light-like curves cannot enter horizon, ingoing time-like curves cannot enter horizon either. So the Penrose diagram for the KMY model goes like this. We think of the collapsing object as composed of many infinitesimally thin shells collapsing at the speed of light. So we were focusing on the region outside the outermost shell, where you have pre-Hawking radiation, namely Hawking radiation appearing before you enter the Schwarzschild radius, represented by this dash curve. You can also study the geometry inside by repeating the same analysis. Between every two infinitesimal shell, you have an empty region in which there is nothing but outgoing Hawking radiation. And in the end, you put everything together, you get the same Penrose diagram as the Minkowski space. In this way, information loss paradox is resolved, or at least alleviated. The information loss paradox, as I mentioned, is a conflict between locality and unitarity. Typically, the story is that you have a parent horizon. Hawking radiation appears outside the parent horizon, which is far away from the collapsing matter. So you need to transfer energy across distance non-locally to preserve unitarity. And here in the KMY model, the infalling matter evaporates into pre-Hawking radiation before it enters the apparent horizon. Essentially, it's the back reaction of the Hawking radiation that prevents the collapsing matter falling into its Schwarzschild radius, and therefore there is no apparent horizon. And also the pre-Hawking radiation is created just next to the collapsing matter, and the collapsing matter is evaporating starting from the outermost shell because of the redshift factor. If you look at the inner shells, there is a huge redshift factor compared with the time coordinate outside. So the outermost shell started evaporating first, and then the second layer, and then the third layer, like peeling on the onion. There's still some mystery remaining, but just like any other proposal for Hawking, for black hole formation evaporation, you seem to need some UV physics to break global charges, because whatever you are collapsing, in the end, the radiation has roughly the same spectrum. So the charges, if you have baryon numbers and other global charges in the collapsing shell, in the end, it's going to be lost. But this is a generic situation. So you may wonder why our perturbative viewpoint was not correct. Namely, people were saying that the Hawking radiation is so weak, it's really extremely weak. How could it have so much back reaction on geometry such that no one can fall into the horizon? Well, in general relativity, perturbation theory can be tricky, because if you have a perturbative expansion in one coordinate system, it's not necessarily a good perturbative expansion in another coordinate system. For a distant observer, the Hawking radiation is indeed extremely weak. So for a distant observer, there should indeed be not much difference between the conventional picture and the KMY model, which is true. So what's different is the difference lies in the experience of an infalling observer. For an infalling observer, if you have radiation near the collapsing surface, or you have no radiation near the collapsing surface, it is a difference for an infalling observer. So the experience for the infalling observer doesn't really have to be exactly the same, although they are still quite similar. There are several important features of the KMY model. Firstly, the back reaction of Hawking radiation is included in Einstein's equation. When we use the outgoing Weidian metric, it already includes the back reaction of Hawking radiation. So it's not like a perturbative expansion in the conventional approach. Secondly, there is Hawking radiation before the appearance horizon, which we call pre-Hawking radiation. And typically in the standard discussion of conventional model, you divide the black hole formation process into the first part, which is the collapse of classical matter without Hawking radiation, and the second part is a black hole with horizon and Hawking radiation. But here, what's crucial is the transition from collapsing to the end. So it turns out that the transition process from no horizon towards horizon is very crucial if you include the effect of pre-Hawking radiation. Now, the back reaction of pre-Hawking radiation keeps the collapsing surface above the horizon at finite distance. That's how nothing can fall into the horizon. Let me go into a little bit more details on this point. So you can consider the ingoing light trajectory. Say you have a particle with the coordinate r given by capital R of u, and this is the light curve equation. And the Schwarzschild radius is shrinking with time given by the usual formula for Hawking radiation. And you can see easily that as r decreases towards the Schwarzschild radius, it's going to be stopped at a finite distance away from the Schwarzschild radius by this much, according to this equation. Sigma is a constant determining Hawking radiation. And therefore, you can say that every collapsing surface would collapse until it stays just outside its Schwarzschild radius at finite distance. The mechanism can be understood this way. When you have Hawking radiation, the larger Hawking radiation you have, the faster the Schwarzschild radius is going to shrink, making it harder for the collapsing surface to approach to the Schwarzschild radius. And as a result, if you calculate the energy flux at the collapsing surface, you see that it's not going to diverge. Even though you do get a very large blue shift factor, so that the energy density is much higher than without the blue shift factor. But the Hawking radiation is just too small, so that even after you multiply it by the large blue shift factor, you get a very small energy density. And therefore, even if you are staying on top of the collapsing surface, you are not going to feel like you are burnt, even though we are extrapolating the classical energy flux back to the surface of the collapse. And mostly this is because of the previous page we mentioned that there is a finite distance keeping you away from the Schwarzschild radius, so that the blue shift factor doesn't really diverge, but it's finite. So to summarize, this is the difference and common points of conventional model and KMY model. In the conventional model, you typically do a fixed background calculation. Usually you take the Schwarzschild solution or a simple collapsing process. And in this background, you calculate energy momentum tensor in quantum field theory. But in KMY model, you include the back reaction of the quantum stress energy tensor from the very beginning. So that's the difference. The same common point is that they both want to say that the initial state of the whole universe is the Minkowski vacuum at past infinity. You start with the same initial state. Although what you really get as a result of this initial condition could be different depending on how you deduce the evolution of the initial state. Outgoing energy momentum tensor for the conventional model is taken to be finite on the future horizon, vanishes on the past horizon of the Schwarzschild solution. And then you have negative energy just outside the horizon. This is the Early vacuum. In the KMY model, you have outgoing energy momentum tensor that's equivalent to classical radiation, just outside the collapsing surface. But it's finite, it doesn't diverge, and energy is positive everywhere, so weak energy condition is violated by the conventional model, but not by the KM1 model. So essentially, you have a different regularization scheme for the calculation of energy momentum tensor in these two approaches, and also the end result of time evolution from the same initial state is different, argued to be different. Let's continue this comparison. Hawking radiation only appears at distance in the conventional model. Near the horizon, you have negative energy, and KMY model Hawking radiation, here I mean Hawking radiation, you have it at a distance. This is true for both. You have the same Hawking radiation at the distance, but the Hawking radiation at the near the horizon is different. In the conventional model, you have a horizon. In KMY model, you have no horizon. Conventional model has the information loss paradox, inconsistent with unitarity or locality. KMY model is consistent with unitarity or locality. In the conventional model, you would have the problem with firewall if you insist unitarity. In KMY model, you do not have that problem. And then for both cases, there is super Planckian problem, namely the Hawking radiation we see at a distance has a super Planckian scale frequency if you trace it back to the inside of the collapsing sphere. In the conventional model, you would always have complete evaporation. In the KMY model, it depends on the collapsing shell. If you have a very thin shell, then the Hawking radiation stops. In the end, the Hawking radiation approaches to zero, and in the end, you get a classical black hole. If you have a continuous distribution of energy in your collapsing shell, then you get the same similar behavior as conventional model in the complete evaporation within finite time. Okay, so my time is up. So we can study the geometry inside, and let me skip that part. And also let me show that there were other people who also proposed that there is no event horizon, although most of them proposed that there is a time horizon. So to conclude, we have a self-consistent picture of black hole non-formation evaporation, which does not have the information loss paradox. Although what remains to be done is perhaps the regularization of energy tensor. And also, we see that to resolve completely the information loss paradox, we still have the global charge conservation problem, which needs UV physics. Thank you.
What about the heat capacity in both cases? The behavior is the same? Or in one case, the heat capacity of the black holes in each case, in each mode, they behave the same everywhere? Or?
It's essentially the same.
Just to clarify about the information loss paradox. So in case that there's incomplete evaporation, so we still have a black hole. So the information paradox is still there, right?
No, in the KMY model, if you get a black hole in the end, it's a classical black hole. So if there's no Hawking radiation, there's no information loss paradox. You just have the information not accessible to you. So like in cosmology, you have everlasting accelerating universe. You don't say it's information loss paradox, but there are information that are not accessible to you.
So what's the mechanism which suppress all the quantum effect after you get this classical solution?
Oh, it's just the formula for Hawking radiation. According to KMY model, you use a formula involving a Schwarzschild derivative, which involves some higher derivative terms. so that when you ignore the higher derivative terms, you get the same story as the conventional model. But when you have a very thin shell, the higher derivative terms becomes important, and it turns itself automatically by itself.
Yeah, but I still think of this as a solution in the quantum field of gravity.
Yes.
So how is it? How can I stop the quantum effect around this classical solution?
Right. So the quantum
Do
effect.
you think this is a full quantum solution of the full quantum field of gravity?
It's the low energy effective theory, and according to this way.